Hi guys, in this video we're going to be talking about the concepts that we studied in the previous video a little for what needs to be satisfied for f to be qualified as a function. So we talked about two sets A and B, but before that I'd like to go into what a domain and range is. So domain of a function is basically the set of all first value coordinates. What that basically means is that when you're making a function is mapping a particular element in A to a particular element B according to this definition over here, right? So what eventually results is an ordered pair. So the set of all possible first or elements of the ordered pairs are known as the domain. Whereas the range is basically the set of all the second value coordinates. So in this particular case, we can see that a triangle, a circle, and a square make up the set that consists of all the second order pairs, right? So the domain of F would be a set that makes up 1, 2, and 3 because those are the first coordinates, right? The domain of G, however, would only comprise of 1 and 3 since the element 2 does not really exist in that particular case. What about the range of F? Well, simply put, it would consist of a triangle, a circle, and a square. Because that's the set of the second value coordinates, right? And the range of G is simply a triangle and a circle, as we can see in the above particular case. Let us now talk about the different classes of functions. The first one is known as an injection. That's just a fancy word for a one-to-one function. The condition for a one-to-one function basically says that if two values of the function are similar at any point, basically they're saying that two elements of B, if they're the same at any point, then that would only happen when P is equal to Q. If this condition holds, then the function is one-to-one. These are the examples of the function f and g that we talked about above in terms of mappings. So basically in this case, 1 is being mapped to the triangle, 2 to the circle, 3 to the square. And whereas in this particular case, where we have 1 being mapped to the triangle and the circle at the same time, and 3 is being mapped to the circle. So let's talk about this for a second. Two values of y, when they're equal, then it basically means that the element in A, or the element in X basically, that's associated with it, has to be the same, has to be unique. So basically what they're saying is, for the triangle, when the triangle is equal to the triangle, that's only going to be possible when 1 is equal to 1. So in this particular case, it works. And it works for all values of the elements in B, which means this is one-to-one. But what about this particular case? In this particular case, let's talk about the triangle first. When the triangle is equal to the triangle, there's only one possible value, 1, that can eventually lead to the value of the triangle, right? That's not really a problem. So the first case is satisfied. But let's talk about the circle over here. When the circle is equal to the circle, then basically when this is going to be possible is when you're going to have 1 and you're going to have 3. Basically, what I'm saying is that 1 is being mapped to the circle and 3 is being mapped to the circle. And they are not equal to each other, which basically goes against the rule we just studied. When two function values are same, or basically the circle, the value, the function value that's present over here, it's being mapped onto by two different values of x, or the values of A, then this condition is not correct, which means this is not one-to-one. Let's talk about another class of functions, which is known as a surjection, which is again just a fancy word for an onto function. What an onto function suggests is that for every value that is contained in the set B, and let me just clarify, set B is where the values of A are being mapped onto. So 1 is being mapped onto the triangle, 2 is being mapped onto the circle, and 3 to the square. So an onto function says that for all values in B, there has to be a link made with the values in A, which is saying that no value in here should not have a value in A. Basically, a mapping should exist for all particular values that are present in B. Let's come up with a counter example for this case. If we were to have something like 1, 2, and that would be mapping onto the triangle, square, and a circle. 1 is being mapped onto the triangle, 2 to the circle. But there's a value, which is basically a square over here, that does not have an element in A, which basically states that this is not onto. Let's now talk about the third class of functions, which is perhaps the most important class that we're studying at this point. An inverse function. They're basically known as bijections, which is another fancy name for an inverse function. And for a function to qualify as an inverse function, it has to satisfy two conditions. The first one being it has to be one-to-one, which is basically an injection. And the second condition being that it has to be an onto function, which is known as a surjection. So if I were to make a particular example in this case, that is mapping the coordinates of A to coordinates of B, then I would probably have something like this. And let's have a star shape as well. So 1 is being mapped onto the circle, 2 is being mapped onto the rectangle, 3 is being mapped to the triangle, and 4 to the star, the new shape we just made. So let's check if this is a one-to-one function. For particular values in B, we need to check if it is uniquely linked to all values in A, basically. So we can see that the circle is uniquely mapped through 1, which means there's just one link to this. There's one link to the square, one link to the triangle, and one link to the star, which means it is a one-to-one function. Let's check if it's onto. Are all the elements in B being satisfied? Are all the elements in B being used by all the elements in A? But the second condition really doesn't matter. What matters is that all the elements in this particular set are being mapped by particular elements in A. They do not need to be covered in A. So for example, if I had 1, 2, 3 over here, right? And 3 was being mapped to the star, it would still be onto, but it won't be one-to-one. So in conclusion, it's a one-to-one function and onto as well, which means it's the inverse to this function exists. And actually, if you think about it, the inverse of this function would be a function that maps B to A. This is another important concept. So you'd have the same elements, actually, you'd have the opposite elements. You'd have a circle, a square, a triangle, and a star here, and they would be mapped to these elements. So that's what an inverse is. You basically invert the function. So if f, it's right over here, if f was a function that mapped elements of A to elements of B, then f inverse, in this case, would be a function that maps elements of B to elements of A, provided these two conditions hold. That's pretty much it for this video. We're going to talk about the specifics of the different kinds of functions you can get when you apply particular operators of them in the next video.